Alright, so, so far in these videos, we've gone through many, probably, types of new math for you, talking about fundamental equations, Legendre transforms, Maxwell relations. And so that could be a lot of information to try and memorize all at once. And so, in this video, what I want to show you is actually a quick mnemonic for, you don't have to memorize all these equations directly, but what you could do is you can memorize this mnemonic, and it will help you derive all the equations that you want very quickly. Okay? And so we call this mnemonic a thermodynamic square. And so what the thermodynamic square allows you to do, it allows you to quickly derive fundamental relations, or fundamental equations, I guess. And those Maxwell relations really quickly. Okay? Alright, and so we call this mnemonic a thermodynamic square. And there's two versions of it depending on if you use A or F for your Helmholtz energy. Right? And so for the thermodynamic square, its structure looks like this. So it's like a 3x3 grid. Where you have arrows stretching across like this. Okay? So this is what it would look like if you used F for your Helmholtz equation. Or if you used A, it would look like this. Okay. S H and P, arrows going the same way. Okay. And so essentially the structure of this thermodynamic square is you have all your different energies kind of in the middle of a column or middle of a row. And then you have all the canonical variables for those energies, flanking them on both sides. And then you have the coefficient for those conjugate pairs, or on the other side. Okay? All right, so let me write this out. So to construct a thermodynamic square, here are the steps. So you would draw something like this in this order, with the arrows pointing this way. And this is how you would use it. So the first step is you pick an energy. So let's say you wanted to derive the fundamental equation for internal energy really quick. So what you would do is you would pick an energy in the center of a row or column. And so U, H, F or A, or G. And then that energy, that's going to be the differential on the left-hand side of your equation. Okay? So we're picking U. That'll be du on the left-hand side. Okay? And so looking at U, well, actually, let me just write out all the steps first and then show you the example. Okay? Step 2. The two letters on each side of the energy will be the canonical variables. And so these are the variables that will be in the derivatives. be the differentials on the right-hand side. Okay, the third step is the letter diagonal from the canonical variable that's going to be the coefficient multiplied by the differential. So it's the coefficient of the differential. All right, and then step 4 have to deal with that arrow. If path from canonical variable to coefficient is in direction of arrow. So if you go from tail to head of the arrow, then the sign of the coefficient is positive. If it's the opposite, then the sign is negative. Okay? All right, and so the first 4 steps just deal with deriving the fundamental equation. The last step is for deriving the Maxwell relation. So here, the coefficient and the canonical variable in same row / column provide Maxwell relation. All right. And so I'll show you how that would work. Okay? And so, like I was saying earlier, let's start with just one that's we know. Internal energy. Okay? All right, so here, if I zoom out, we pick U, and so on the left-hand side of the equation, we would write du. All right, flanking du, or flanking U, are V and S. And so we would write S and V in the differentials. Then, from each of these canonical variables, we would follow the arrow directly diagonal to it to find the coefficient. And so for S, diagonal from it is T. And then for V, diagonal from it is P. When we went diagonal from S to T, that was in the direction of this arrow. So T here is going to be positive. But when we went from V to P, we went opposite the direction of the arrow. So that tells us P is negative. All right? And so that's how you use the thermodynamic square to derive the fundamental equation. Now for step 5, this is what we do here. Okay? So here step 5 is saying that the canonical variable and the coefficient in the same row column provide the Maxwell relation, right? So here T was a coefficient and V was a canonical variable. And so for our Maxwell relation, we would write dt dv, and this would be at constant S. Okay? That would be equal to, now we go to the other side. Coefficient is P, canonical variable is S. So dp ds, and that would be at constant V. Okay? Right, and so from that, And there's also the negative sign. We can't forget that. Okay. All right. And so just by using that thermodynamic square, we're able to just get the Maxwell relation really quickly. We don't have to think about taking second derivatives or remembering what the partial derivatives are. All right, so that's what we did for U, but now let's try one that we're less familiar with. Let's pick the Helmholtz energy. So for Helmholtz, it's here, dA. On each side of it are the canonical variables t and v, so dt, dv. If we go diagonal, the coefficient for t is s, the coefficient for v is p, and in both cases we went against the direction of the arrow, so both of these are negative. Okay? Alright, and so now, to get the Maxwell relation, here we look at the coefficient p. We see that it's in the same column as the canonical variable t. So dp dt, and coefficient was a conjugate pair with v, so it's going to be a constant v. There's a negative here. All right, and then on the other side, coefficient was s, canonical variable was v, and this coefficient was originally paired with t, and so the Maxwell relation here is now going to be ds dv, ds dv at constant t. Now it's also a negative, but the negatives cancel out. Okay? All right, and so from the thermodynamic square, we could just quickly derive the fundamental equation and Maxwell relations.